Think about some of the most extreme places imaginable. The inside of a jet engine or the core of a chemical plant. We rely on materials that can take an incredible amount of punishment. Heat, pressure, you name it. But finding stuff that's tough enough is a constant battle. So how do we actually create surfaces that can survive these environments? Well, the answer involves a process that's as precise as it is powerful.
The solution looks like something straight out of science fiction. It's called high-speed laser cladding. Basically, a super powerful laser melts a stream of fine metal powder right onto a surface. It's kind of like 3D printing a brand new, ultra-resilient skin onto an existing part, one tiny layer at a time, creating a perfect bond.
And the powder they use for this is often a super alloy called Inconel 625. It's this nickel-based beast that's a total powerhouse in aerospace and energy. This whole technique lets us put its amazing properties exactly where we need them most. But, and this is the really cool part, the true genius of this whole process isn't just the laser itself, it's the intense heat it leaves behind.
Yeah, the real secret is in the invisible aftermath. It's what happens in those moments after the laser is already moved on that completely transforms the material into something new. This whole effect is called thermal cycling. See, as the laser lays down new tracks right next to each other, the first track gets blasted over and over again with intense leftover heat from its neighbors. It creates this wild thermal roller coaster.
And you can see just how wild that ride is right here. On the very first pass, a single spot on the material just skyrockets to nearly 1900 degrees Celsius. Then the second pass hits that same spot at an incredible 1050 degrees. After that, the peaks get a little smaller, but the material is still getting heated and cooled repeatedly in just fractions of a second.
So this led researchers to a really crucial question. Is all this thermal chaos actually a good thing? I mean, does it forge a stronger alloy? Or does this constant stress actually bake in tiny microscopic flaws that could cause it to fail later on?
To get the answer, they had to go microscopic. They had to peer deep, deep inside the material's atomic structure to see exactly what was changing with every single one of those heat cycles. And the comparison here is pretty striking. On the left, you've got the structure after just one pass. It's relatively simple, with these clean, column-like crystals. But now look to the right. After 10 passes, wow, the whole structure is way more complex and tangled up. You can literally see the material evolving right before your eyes. So what are we actually seeing here? Well, after 10 cycles, those original crystals have gotten whiter. But the real game changer is that dense network of new hard structures. They're called Laves and MC phases that is formed between the crystals. Just think of it like super strong mortars suddenly appearing between bricks, locking everything tight.
And something else is going on too. That intense heat is actually causing iron atoms from the steel underneath to start migrating upwards into the Inconel coating. So with each heat cycle, the coating's fundamental chemistry is actually changing from the bottom up. It just keeps getting more complex.
All of this digging at the microscopic level led to a completely unexpected discovery, a result so counterintuitive it basically flipped the entire understanding of this process on its head.
I mean, your gut instinct would tell you that repeatedly heating and stressing a metal would just introduce more and more defects, right? More little imperfections in its atomic structure. It should get weaker or maybe more brittle, but that's not what happened at all.
This graph right here shows the big twist. That line represents what's called dislocation density. You can just think of dislocations as tiny little wrinkles or defects in the atomic fabric of the metal. After the first pass, yeah, the density is high. But look what happens at cycle 2. The number of defects just plummets. It actually heals itself.
So, why? Well, that second thermal cycle, at over 1,000 degrees Celsius, is so hot that it acts like a perfect annealing treatment. Annealing is the process that relieves internal stress and lets the atomic structure kind of repair itself. It smooths out those wrinkles and makes the material more uniform.
But here's the second part of the twist. After that one healing pass, the next 8 cycles are cooler. Now, they aren't hot enough to anneal, but they are hot enough to introduce new stress, and this causes the number of dislocations to skyrocket. These new defects all tangle up, creating this complex web inside that makes it incredibly difficult for the atomic layers to slip past each other. And that is the secret to its amazing strength.
So this incredible journey of damage, followed by healing, and then followed by strategic re-stressing at the atomic level, it all results in a material that is dramatically harder and stronger than when it started.
These heat maps show you the final result beautifully, the microhardness of the material. As you go from one thermal cycle to 10, you see the color shift from those cool blues and greens all the way to hot reds and oranges. This isn't just a pretty picture, it's a direct visual measurement of the material getting tougher with every single laser pass.
So how much tougher are we talking? The hardness increases by about 45%. That's a massive gain in performance, and it's all done by precisely controlling the heat that a laser leaves behind.
So this entire incredible process can be boiled down to a simple 4-step recipe. First, you lay the foundation. Second, you heal it with a blast of super high heat. Third, you strategically damage it with lower heat to build up that web of strength. And the final result? A perfectly engineered, ultra-hard surface.
And this matters a lot because it leads directly to stronger, lighter, more efficient parts for everything from jet engines to industrial tools. But even bigger than that, understanding this process gives scientists a blueprint for designing totally new materials, ones that can be precisely tailored for any job you can think of.
It really leaves us with a fascinating thought, doesn't it? We've learned to use not just a laser's light, but its leftover heat to literally write a recipe for strength right into the atomic structure of a material. So the question now is, what other impossible materials are we going to be able to design one laser pass at a time?